So, very good morning to one and all present. Myself, Dr. Tanmay Roy Chaudhary, and I'm going to be the host of today's event. Today we are gathered here to celebrate the International Pi Day. It all formally started in 1988 by Larry Shaw. He was an employee in the California Science Museum. And about pi is everywhere. I hope you have seen the video. It's a wonderful video that is playing behind. So pi is everywhere in nature, starting from the orbits of the planets and satellites, the double helix of the DNA, the waves of light and sound, to the most weirdest equations in physics, that is the Heisenberg's uncertainty principle, to the engineering design, the design of cylindrical vessels and for the aircraft, or if you want to design a video game, everywhere there is pi. But the irony of the situation is that nobody knows the exact value of pi, so it's unknowable. And the fun part is that the most rational minds in this world are putting their heads to decode the secrets of the most notorious irrational that ever existed. And today, it's no different. We are going to poke that notorious irrational number today, followed by the presentation by you people, your ideas on the applications of mathematics in everyday life. And I wanted to mention one more thing. Today is also the 144th birthday of the genius, that is Albert Einstein. So with that, I invite our very own principal sir, Professor Abhijit Lahiri, to deliver the welcome address. Sir, please.
Good morning, students. It's very interesting that we are observing International Pi Day and it's being organized by Basic Science Department of our college. I really express my thanks to them for having this idea, and finally the program is going to start now. So thank you, sir, for carrying this idea, and it's really important to know something or many things about pi, because I hardly know something about pi. So the information about pi and what its origination, how it works, where it is applied, and how we find it in mathematics and all other applications, these things are really important, and I hope that this session will be very interesting for all of you, and we will gather much knowledge about it. So I wish all the best and all success of this program. But I have one question to the organizer. Please show the slide. Where the photo of Professor Milan Chakrabortty is there. So the logo of MCKVIE and the logo of NAC, has it been designed on the conception of pi? I don't know, but I found it, they are incomplete. Okay. So thanks a lot. Enjoy the session.
Thank you.
Thank you so much, sir. To set the stage for the competition, we have the keynote lecture. The lecture will be definitely on pi. You are going to dive into the secrets, and we are going to know much about pi. And the lecture will be delivered by our very own Mr. Milan Chakrabortty. He is the assistant professor in the Department of Basic Science. He has done his MSc from Kazi Nazrul University, Asansol. He is a first class first and was awarded a gold medal in 2016. He is pursuing his PhD from Kazi Nazrul University and his topic is inventory control and supply chain management. He has done 2 publications in reputed international journals. With these few words, I would invite Mr. Milan Chakrabortty to deliver his lecture, and I hope this is going to be a damn interesting one. So,
good morning, everyone. So, as all of you can see, the title of this lecture, and which is the uncovering the secrets of the number pi. So that means today we will know that pi more closely. So from where actually it originates and to in which actually areas it will be used. Actually it is being used. So now you can see that date and which is the 14th March. That means this is 0, 3 and 14. And these 3, 14 actually are the first 3 approximate digits of the pi, which is the 3.14. So that's why this date is selected, and this day we celebrate the International Pi Day. So now, first I think all of you know the definitions of the pi, and which is the definitions. So you can see that this pi is a famous mathematical constant and which is equal to the ratio of the circumference and the diameters of a circle. I think all of you know that. Also this pi, and mostly whatever may be the size of the circle, if it is small or if it is very big, this ratio is always same. So that's why this is a mathematical constant. And this pi is also the 16th letter of the Greek alphabet and also present as the first letter of the Greek words periphery or the perimeters. And now we come to some properties of the nature of this pi. Why this pi is so notorious? So first, Konmaisa already says that the irrational nature of this pi. That means you can't express this pi by the fractions of 2 integers. And not only that, its decimal presentation never ends and never actually enters to a permanent repeating patterns. That means you can't find any pattern in its decimal presentations. And this thing, this irrationality, first analytically proved by the Johann Heinrich Lambert, the famous mathematicians. And after that in 19th century, Hermites, Charles Hermite and then Marie Cartwright and Johann Nivens and also the Nicholas Varouki, actually they give some simple proof because these proofs are not so easy, analytically the proof of the irrationality. And they actually gives some simpler proof what a students with only some prerequisite knowledge of basic calculus can understood. And after that, not only this, the irrationality of pi, this pi has another very interesting property and which is the transcendence. Transcendental means actually you can't find the pi as a root of some polynomial equations whose coefficients are rationals. You can see these equations, first is this x square minus 2 is equal to 0, or the below these equations, actually both equations are polynomials. And root of these equations, the first, for the first this is root 2 and for the second this is the famous golden ratio which comes from the Fibonacci series. This is also another famous mathematical constant, the golden ratio, mathematical ratio. Okay, so these two numbers actually rational number. But number comes from some polynomial equations. But you can't derive pi from this type of polynomial equations. And that's why pi is also a transcendental number. But this actually proves, it's done by the Ferdinand von Lindemann and first in 1882 and by the continued fractions. So you can see the continued fractions of that pi. Actually every rational, irrational numbers and even numbers can be presented as a continued fractions. And this is the pattern of this fraction of pi. And you can see no obvious pattern is there. First you can see the 3, then 7, then 15, then 1, then 292 and then again 1, 1, 1. No obvious pattern is there. But if you see the pattern of this root 2 or 5, actually you can see that in root 2 there is a pattern of 2, 2, 2 and then again 2. And in case of the golden ratio 5 there is also 1, 1, 1. Again all of these terms are 1. But in case of the pi, there is no relevance, there is no obvious pattern, and that makes this pi as the transcendental number. So not only the irrational, it is also a transcendental number. And its simple expression also actually can show you any obvious patterns. So this 3, 22, 7, 3, 3, 3 by 106, 5 actually comes from. If you see this pattern closely, first digit is 3 and then if you take the second 1 and 7 together, this will give you the 22 by 7. And next if you take 1 and 15 again, you will get 3, 3 by 106. That means if you cut this continued fractions term by term, you will get some approximation of the pi. Next, suppose, now the question is, before discovering the calculus, you all know what's calculus, to find the area or the volume under some actually curve, actually all of us actually needs the calculus, which is actually calculated by the area under the curve. Now before invention of the calculus, mathematician or the scientist use the approximation, which is the polygonal approximation. That means we approximate everything to the polygon and then we calculate the area under these polygons. And from that, a famous problem arrived, the squaring of the circle. Is it possible to make a square from the circle? Can we make that? Because every polygon can be actually geometrically converted to a equal area square. But is it possible in case of the circle? So if it is possible, then you can geometrically construct pi. That means the side of the square, which is root pi. So if root pi is geometrically constructible, then obviously pi is geometrically constructible. This problem is actually disproven. That means mathematicians Pierre Wenzel first proved that every figure, every line you can draw geometrically actually roots of some algebraic equations. That means they are actually algebraic numbers. So if it is a transcendental number, you can't draw this by using only a compass or any scale, that means any strategy. And it is proved in 1882 when this Lindemann actually proved the transcendental nature of this pi. After that, everyone know that whatever we may try, we can't actually draw this square from a circle. But many mathematicians actually struggle to find this approximate area of this square. And some of them are actually first this Adam and Kuczynski, who actually geometrically find the correct up to 4th decimal digits by these constructions. And following that, Jacob T. Gelder also find the 6th decimal approximations of the pi, and this is actually the constructions. And not only these famous European mathematicians, our mathematicians, Srinivasa Ramanujan, Also find the most correct decimal places of the pi by geometrically construction of the squaring problems. And this is the formula behind that, and this is the constructions you can see. Srinivasa Ramanujan actually calculated this pi, and which is correct up to 8 decimal places, and this is by the geometrical constructions. Now, not only in mathematics, this all our previous things are already actually in mathematics. Not only in mathematics, you can, if you say the history, that means the literacy. See, this is the famous picture of the Vitruvian man, and due to the Leonardo da Vinci, and before that there is a prototype by the Giacomo Andrea, and in both this picture you can see there is a relation between the circle and the square. Actually this is related to the squaring problem. And here Leonardo da Vinci actually described the navel of a human as a center. And then if we take these stretched hands and if we actually create a circle, this area of the circle and the perpendicular distance from the sole to the head and this outstretched hand, these two will be equal and this will make a square. And area of these two will be equals. So that's why not only in mathematics, in the history, everywhere you can see the pi and behind all of these things. Okay, now we see some developments of this pi, where this pi comes from, and is it pi from the beginning or we added this? So if we see the history of the pi, so first assumption, actually we divide it into some era, first the assumption era, and then we come to the polygonal approximations era, and then the infinite series era, and after that we come to the now current, which is the computer era. So from the beginning, actually we need some values of pi. Wherever actually someone suppose creating some wheel, actually he need that constant, he have to assume some values. That's why he can prepare these circular shapes. So that's why from the Babylons and the Egypts, first say the Babylon suppose, and here clear tables indicate that the value of the pi is equal to 3.125, and after that in Egypt also value of pi is assumed as the 3.16, and not only in this age, also in the Sulva Sutra of our Indian mathematics, and there are basically 4 Sulva Sutras, and this actually contains the rituals of the Indian cultures, and where also the circle, area of the circle is used. And there are 4 major Sulva Sutras which are actually Buddhayana, Manava, and Apastambhava, and the Katyayana. In all of these Sulva Sutras, there are many types of approximations of pi, and as 3.0881 in this type of approximations we can find. And after that age, we comes to the polygonal approximation era. Before that, everything is just assumption. So the first man to prove something is the Archimedes. And Archimedes first used the polygonal approximation, the polygonal bound of this circle. And by using some polygonal approximations, actually by using 3, 4, 5, 6, and in this way 96 sided polygons, and they measured that the bound of pi is in between 3.1408 to 3.1429. This upper bound of this Archimedes approximation is still used up to now. We use this approximation for the physical calculations, this 22/7. After that, so many digits are found. Actually, we are finding also, but now also we use this number 22/7. Now, if you see this slopes, not only the Archimedes but also in India by the Aryabhatta in his Ganita Pada, actually he described that Chaturadhikam Sata Ashtagunam and Drashastasta and Sahasranam. So this is means that Chaturadhikam Sata. Chaturadhikam Sata means 100 plus 4. Add 4 to the 100 and then Ashtagunam into 8 and then Dwa means Drashta. Drashta means here the 62. Drashti Tatha. So Dwasasti. Dwasasti means 62 in the Sanskrit. And with the Dwasasti Tatha, Sahasranam means 1000. That means 62,000. Now add this 100 plus 4 into 8, then 62,000. And below you can see the Ayuto. Ayuto Dayasta. Ayuto Dayasta means, Ayuto means the 10,000s. Daya, that means double of that. That means 20,000. And Biskambhaya, Biskambhaya, Bistara, actually these are used to indicate the diameters. And Asamma Bitra Parinaha, that means this value gives you a approximate value. Actually, Aryabhatta mentioned this value as approximate value, not an exact value. Actually, know these things, that this value is not actually value. This ratio will give you some approximate value, and this is the first reference of the irrationality of the pi we can take. And after that, many mathematicians and scientists take many numbers of sides of polygon to approximates of the pi, and this is the chronology of that. They take many sided polygon, 3072 sided polygon, 12280. Actually, this you can do that by hand. They make some algorithms, polygonal algorithm. After that, they use that to find the value of the pi. And after this chronology, you can see here the Wilcox's radius. You all know here actually. This radius means the Snell's law or the fraction of light. This Snell's also find the 34 digits of pi by the polygonal approximations. And finally, in the polygonal approximation era, Christopher Gegenberger actually find the 39 digits using a 10 to the power 40 sided polygons. This is a huge number, 10 to the power 40 sided polygons. We can approximately take it as a circle. So now this number is the geometrically actually discovered the maximum numbers. After that we comes to the infinite series era. After developing the infinite series, everything was changed. Now we can find more number of digits of pi. Now in this infinite series era, one name I can remember, and he's a famous mathematician who is Madhava. I think all of you know that. No, Madhava? The Kerala mathematicians, that's why we don't know actually the Indian mathematicians. But we have to know that Indians have contributions in the mathematics. But due to connectivity, many of the mathematicians actually we don't know these mathematicians. So one of them is the Madhava. And the known series, the sine series or the cos series or the arctangent series, this series was discovered by the Madhava in 14th century in the Kerala, in his Kerala astronomical school. And you see that, so these are the modern notations of the series. This series was discovered in the 14th century by the Madhava or his followers. And this series again rediscovered in the European country by the renowned some mathematicians or physicists like Newton, Gregory, Leibniz. They again rediscovered this series because there is no name of Madhava this time. But currently, due to the priority of the Madhava, these series are known actually sometimes the Gregory-Madhava series or the Newton's-Madhava series. But before it, actually we don't know anything. Now this, not only that, Madhava also gives a first converging series of pi, and whose 21 terms gives the 11-digit accuracy of the pi. And after that, in the 17th century, actually, European scientists rediscovered this series and they used this series to find the value of pi. So there are also some chronology, and the Newtons used this type of series to find the 16-digit approximations, and then using the Gregory-Leibniz series, and which is now the also Madhava series also, and by putting the z is equal to 1 by 3, because we all know that in the arctangent series, if we put z is equal to 1, you will get pi by 4. And in this arctangent series, if you actually, this is the Cannon series, in this series if you put 1, you will get the pi by 4, and from where you can actually approximate the pi. But z is equal to 1 slowly converges. That's why next this Abraham Sir used this series for the 1 by root 3 to set the record of 71 digits. And this is the breakthrough of this 39 digits approximations of the polygonal approximations. And after that, this type of series is used in combinations. This John Mackin used some combination of arctan series, and after that many scientists use this type of Mackin-like formula to find many numbers of digits. Then 200 digits, then British mathematician William Strange 607 digits, but actually he made a mistake. And 528 digit, and that's why the subsequent digits are actually incorrect. And finally, 620 digits approximation, which is the maximum approximate digits using this infinite series, is due to the Daniel Ferguson's. And after that, our computer era start. Then we use the computers, and this is the best approximation without using any of the computing aids. After that, we come to the computer era, and you all know that by using computers and by using this infinite series and using algorithms, we can find more numbers of digits. And this is the chronology: first 1949, then 2037 digits, and in this way, using arctangent series, 1 million digits of record reached by the Martin Boer. And after that, the revolution happens. Some additional developments in the field of computer. First, the discovery of new iterative algorithms, and mostly the invention of fast multiplication algorithms, because most of the computer memory actually goes to the multiplications. So after inventions of this new multiplication algorithm, now it takes minimum time for the computations. And now, using that, Japanese mathematician Yasumasa Kanada actually made many records between 1995 and 2002. But this iterative algorithms needs much storage for the calculations, and which we actually don't need in the infinite series. But here we need more storage. So that's why, again, the modern approach is actually invented. And what is the modern approach? Now currently, pi program does not actually use the exclusively iterative algorithms. It uses the infinite series also. Together with the infinite series and the iterative algorithms, now we find the value of pi. And again, you can see Srinivasa Ramanujan. And actually, this is discovered in 1980, but actually Srinivasa Ramanujan gave this series of pi in 1914. And not only that, actually he gives many approximations formula for pi. He does not give any proof of that. Actually, he says that it comes from a dream. and I have no proof of that. But using this formula and adding each term, you can find 8 more correct digits of pi. Just add one terms, you will get 8 more digits. And using this algorithm, Bill Gosford first used this to find the value of pi, and he reached 17 million digits in 1985. 17 million digits in 1985 using these Ramanujan's algorithms. And after that, not end here actually, after that Chudnovsky brothers used these Ramanujan algorithms to improve. And he discovered another Ramanujan's like series which actually give the 14th digit in adding each term. Not 8 digits, more than that, and up to now, this algorithm is used. Also now we are using this algorithm for finding the value of pi. And using these algorithms, first 1 million digits, and due to obviously that would be Chudnovsky brothers because they developed these algorithms. So they find the 10 to the power 9, that means 1 million digits of pi. After that 10 trillion digits due to Alexandrian Kondo, and now this is the maximum finded digits of pi, and due to Eva Haruka Iowa, and this is 100 trillions, 10 to the power 14, you can imagine these digits. Her length, actually what is the length of that, you can take it infinite. So actually this Eva Haruka Iowa, and this is the program, but it's called the white transfer program. And using this program, not only pi, many other irrational numbers is also found, like the pi or the root 2. Actually many minds, actually curious minds, finds this number to set some records using this pi white transfer program. And this is the configuration of this machine. You can see there is 864 GB RAM. And memory used for finding this is actually 515 TB. 515 TB memory is used to find these values. And these are the last 100 digits of pi, what we know. Actually there is no last digit because this is irrational number. But we know actually this number is, last digit is what? 0. Okay, that means after so many discovery again we reach to 0. This is 10 to the power 14 digits, but everything comes to 0. So obviously many numbers will come again, it will not stop here. And now we have another question. It is very interesting. That means why it is pi? Is it pi from the beginning? Pi is not actually denoted in the clay table of the Babylons or in the Egypt. There is no pi, there is some value which is called the circular constant. The value of the circular constant is that. Value of the circular constant is that. So not the pi. So from when we started to use this pi? In the earliest, pi is used to represent the semi-perimeter of a circle. And together with the diameter delta or the rho as a ratio, we represent the circular constant. Then sometimes it is pi by delta, sometimes it is pi by rho, and with this we represent the circular constant, which today we know as pi. In 1706, first mathematician William Jones used the letter pi in his works to represent the circle circumference and the ratio of that with the diameter to exclusively represent it by the pi. This is the first one that William Jones used it, but he is not so much popular mathematician, so that's why the rest of the European mathematicians actually not adopt this. And this happens till the 1764 mathematicians used the fractional notations, not the pi notations. After that, you will know that everywhere you can find him. This is the Eulers. In mathematics, in physics, and everywhere you can find the Eulers in every equations actually. And Euler first started using pi as 6.28, not 3.14. In some first beginning works, actually he used not 3.14, 6.28 to represent the pi. After that, from 1736, actually he used pi as a 3.14. And here he wrote that for the sake of brevity, we will write this number as pi. And thus pi is equal to half the circumference of a circle of radius 1. If you take a circle of radius 1, its circumference will be what? 2 pi. And if we take the half of that, it will be pi. So that's the first word where he used pi as a 3.14. And actually Euler is very famous. Euler is very famous in the Eastern Europe. And that's why this assumption or the adoption spread throughout the Eastern Europe and then throughout the universe. We can also now measure everything of the universe by using this assumption of pi. But from the beginning it is not that notation. Sometimes they use the 6.28 also. And that's the problem occur. This is the famous controversy. That means, is this adoption of pi is wrong? Because if you imagine, if you take a full circular rotation, actually we say 2 pi. No? Full circular rotation 2 pi. If we take half, this is pi. If we take the 1/4, it will be pi by 2. So why this type of notations? If we denote the full notations as the tau, then one rotation will be 1 tau, half rotation will be half tau, 1/4 rotation will be 1/4 tau, and also the constant we measure, this is actually the ratio of circumference and what? And the diameter. But actually circle is related to not diameter, first comes the radius. You all know, in the definitions of circle actually it is radius, not the diameter. So if you take the ratio of circumference and the radius, you will get what? 2 pi. Circumference and radius, you will get 2 pi. So if we take 2 pi in every calculation, so it will be better to understand every phenomenon. That means 1 round, okay, 1 tau. If you take half round, half tau. If you take 1/4 round, obviously this is 1/4 tau. But you have started that and it is also running. But some mathematicians actually call for the changes now. And they want to change these notations of pi. They want to use the tau. And while they represent this tau as a 2 pi. And this call is first due to the Bob Palace in 2001, where he published an article and with this heading, this pi is wrong. Wrong in, not in this actually sense, the value of pi is wrong. This adoption is actually wrong. If we take the tau, it would be better. And following this, after that, this is another physicist, Michael Hartle. Actually, he published the tau manifesto at the day of 28 June. You can imagine, 28 June means? This is 628, just the double of 3.14. And in 2001, at that day, Bob, physicist Michael Hartle, who is the founder of the Tau Day, and he published his Tau manifesto, and where he also called for the change of these symbols, change of these adoptions. And Tau Day is also celebrated since 2010 and obviously at 28 June, which is the unofficial holiday. And they called it actually for to be official so that he can make this as an official day. And you can see this Tau Day is equal to 628. Not only that, Michael Hartle also called that called for the renaming of the Pi Day. He want that people should call the pi day as the half tau day. You can imagine that not a pi day, take that as a half tau day. Okay? So that's why we have another solutions. So we don't take pi or we don't take as a 2 pi. So we will take a middle value which is 1.5 tau, 1.5 pi, and we represent this p, and here AU we call it tau. This is the middle value. Okay? And we will take that notations for the rest of our actually papers or everything inventions. Is it better? Obviously not. So we can change the notations in just 1 year or 2 years, but actually we can start using tau. Many mathematical softwares like the MATLAB Mathematica already introduced tau as a 2 pi, and it is going to be actually produce some larger movement in the futures. So now another questions after this actually long lectures, you all can imagine that why we need so many digits of pi. Okay, why?
For better application.
Well, we actually don't need that. Why for better accuracy? We know actually that pi actually operates. But we are calculating, so why? This is the question. So first of all, you can see the font heading. So for the most numerical calculation, we will only need a sufficient number of, a handful number of digits, and which is the 39 digits. By using only 39 digits, we can perform any cosmological calculations, any. And that gives the accuracy that actually necessary to measure the observable universe to the accuracy of one atom. That means we don't need more than that number of digits. Actually, NASA also use only 40 digits for every calculations, for every space calculations, and you get the accuracy. So what? First of all, the first reason is our mind. We want to set record. We want to be the headlines of the news, because this type of records will bring you to the headlines. So that's why this is the first reason. People never wins. And secondly, this is the more practical ways. Practically, to measure the accuracy or the computation speed of a computer, this pi algorithm is used. That means using these pi algorithms, you can check the efficiency of a computer. Is it good or not? Is it can perform accurately or not? You can actually check that by using the pi. In fact, in 1986, one pi calculating program actually observed some hardware problem in the Cray 2 supercomputers. And this is due to the pi algorithms. So obviously you can find this by using only 40 digits of approximation or algorithms. And since this is irrational transcendental numbers, so its randomness is better than any other digits. So that's why pi programs are used to test the supercomputers or many other advanced computers. So not only this, we have also one question which is not solved. Mathematicians analytically proved that this number is transcendental, this number is irrational. Again, one question needs to be answered, and which is the normality. Is this pi normal? This is another term. So what is normality first? Normality means, suppose you have an infinite presentations of decimals. So there are digits starting from 0 to 9. That means there are 10 digits total. Now normality says that not a single number appears more probably than the others. That means every number should appear in a probability of 1 by 10. This is called the normality. 1 will appear in the probability 1 by 10. 0 will appear in the probability 1 by 10, and this is the normality question. And obviously it is a statistical process. You all know that how probability and statistics works. Rather than analytically we can prove it numerically. And For the numerical we need digits. Up to now, whatever we know about the pi, this 100 trillion digits, using this, mathematicians and scientists observe that there is no abnormality in pi. That means it passes all the statistical randomness test and also the test for the normality. But maybe in future we can actually discover some abnormality. So that's why we are discovering again and again. Maybe at some point, so it will stop if someone can prove this analytically that it is not possible, like the Lambert. But before that, it will not stop. So that's why. So this is the normality, and you can see this type of numbers, and everything will be a probability 1 by 10, and we will actually wait for that when it is solved. And this is not the final page. You can see that this is finally, but this is not the final page. And finally, for the mathematicians, it is like the climb in Mount Everest. One know that they are lazy actually, but using this type of process, actually they can get the satisfaction. And this is like the climbing Mount Everest or the competing a major sporting events. And they can actually shoot the first positions. So that's why it will not end as long as there are humans. Doubtlessly, we will get many other interesting computations of the pi. It will happen again and again. So that's the discovery and the questions behind the pi. After that, we obviously want the usage of pi. And you all know most of the thing, and I think some people of you actually discussed this topic, that what is the usage of pi. But before that, we start with the use of pi. So first of all, in geometry, you can see this every figure, circle, what can be the sphere, this ellipse, this torus, everything actually contains this pi. In the area, in the volume, in everything. And not only that, in the surface of revolutions, in the volume of revolutions, and where the actually circle is attached, you will get pi there. And not only in this region, if you see the use of the angle and if you see the trigonometry, every angles such as sines, every function, sine function, cos, tan, everything. Actually, these functions are functions of pi. That means that they are argumental radians. And this pi plays a significant role in this radian system. But you all know that 180 degree means the pi radian. And general argument of this function, trigonometric functions, are actually pi. So, not only that, this is another famous problem. This is the eigenvalues. Some of you actually familiarize with that problem. What is the eigenvalues? And in the first semester there is eigenvalues. So in real situations, if we take the wave problem, and in wave problem, we can idealize the vibrating string problem by a model, and as a function of f and in the unit interval 0, 1, and with some fixed, suppose bound, like this. You take the guitar, there is at the end point some fixed, actually constant is there, and this mode of vibration actually governed by this differential equation. This is the differential equation, and here this type of problem is called the Sturm-Liouville problem. And these problems have some non-trivial solutions due to some values of pi, values of some lambda, and this lambda is actually called the eigenvalues. So simply the value of lambda for which you will get the non-trivial solution, this is the eigenvalue, and the solution is the eigenfunction. And you will discover that for this type of problem, you will get lambda as pi square and function as sine of pi x. So that's why here is also pi attached. In every string problem, in every vibrational problem, there is attached some pi as an eigenvalue. Not only in this system, in higher dimension you can also see pi as an eigenvalue. Next, take this Gaussian integral. You all know the normal distributions. I think some of you actually don't know that. What is the normal distribution? This is a probability distribution, and mathematicians actually use this to assume the error in any experimental observations. Sometimes they assume that this error actually follows the normal distributions, and this is the expression for the normal distribution, this fx expression, and from the fundamental necessity of this, right, this function, that means this probability distribution function, if you take the integration is equal to 1, you will get this Gaussian integral as a root pi. Again, this area under the curve, this is represented by the root pi. So whenever you will get this type of shape in your real life, for calculation you will need pi. And take this integral. This is the famous Cauchy's integral. In Cauchy's integral, in the complex plane, you can find the area of this type under this type of curve, and using this type of formula, and you can see one thing, that this is not circular shape. Is it circular? This is not circular, but there is also pi. So in fact, if it is not a circle, pi also attached with that. And that's due to a proof of the Morella's theorem, actually result of Morella's theorem, where they state that this integral is invariant under the homotopy of the curve, where we can deform any cells to the circle, and then you can integrate it using the polar integral rule. So, not only in that, again another thing in our real life, take this structural engineering problem. You can imagine, this formula is actually the buckling formula. Buckling formula means the maximum load, axial loads can take by a beam. You can see this type of beams. The maximum load this type of beam actually can take. This is governed by this buckling formula, which is due to again Euler's. And in this formula, you can see that if you actually get the buckling failure, this type of problem will occur in your constructions. So that's why here is also pi inbuilt. That if you miss the pi, you will miss your construction. Then, moreover, not only that, in the Fourier transformation, in gamma function, in number theory, Heisenberg uncertainty principle, and then Stirling approximation, Cauchy's distributions, in mathematics, everywhere, you will see this pi. Everywhere, just take a page, I think probably you will get some pi. And then, pi is not a physical constant. You all know that. There are many physical constants like the gravitational constants, but pi is not a physical constant. It is a mathematical constant. But it appears mostly in the universe or some fundamental phenomena or the principle of the universe due to its relations with the circle and the spherical coordinate system. It appears everywhere. That means you can see these two problems, this physical phenomena. One is the simple pendulum's motion and another is the frictional force due to a viscous fluid, and which is actually acted to a sphere. If you place a sphere in a viscous fluid, moving viscous fluid, you will see this type of frictional force, and both are actually governed by this pi. You can see pi everywhere. And not only that, now comes to some real life problems. In real life problem, actually this length of this, you can see this projector circle. Okay, your 3.5 pin jack. This is again circle. If you measure it wrongly, actually you can put it here. And then in the real life problem, you can see this type of printer we need everywhere in the hospital, warehouse, in the ticket counters. There is a roll of paper. To fit this roll of paper in this particular versions of your printer, you will need to measure that. And obviously in this measurement you will get pi. And then again here, in this refinery, every vessels are actually cylindrical. You all know the volume of the cylinder. What is this? V is equal to pi r square h again pi r. That means to measure the flow, you need this pi. To operate your system, these whole systems, you need to know pi very well. That's why pi is attached everywhere. Now, after the usage of pi, we actually want to set a focus on this problem. This is very interesting problem. Pi memorizing competitions. Pi memorizing competition is another usage. That means you can set a record by using this pi competitions. And also this subject, this is a subject, you can see that. This is called pi philology. And where you can memorize many large digits of pi to set a world record, and this record is actually taken by the Guinness books or Guinness World Records. And you can see the current Guinness Books of World Records is actually due to the Swiss Kumar Sharma, and which is 70,030 digits, and to recite it actually he takes 17 hours and 14 minutes. And it is set in 2015. Till now it is the world record. No one actually break that. And just in these years, just before that, Rajveer Meena also set a record of 70,000, and for this actually you will take the 10 hours. So this is the list of the pi world ranking, where you can see the first position Suresh Kumar Sharma, and then Rajveer Meena, then one person from China, and then you can see again India and India. So actually this problem is very famous in India. Not here actually, but in India, Indians actually want to be always in the top of everything. This is the spirit. So that means you can see here the priority of the Indians. So next, what is the process of remembering? How they actually remember so many digits? How they? So there is also another technique. For the memorizing, there is a technique, and which is produce some story or produce some poems by using this pi. Okay, and this is called the poems, combining by pi and the poem. And you can take an example that now I need a drink, alcoholic of course, and after the heavy lectures involving quantum mechanics. Now see the length of every word. First is a 3, then 1, then 4, then 1, then 5, then 9, then 2, and so on. Every numbers actually represents some digits of pi. So this is one method, but it is not possible by using this method. You memorize 70,030 digits. So they actually use some numerical patterns, number patterns, or the method of loci to memorize these numbers. So it is not only this curiosity stop here. Some pupils actually use these digits of pi to make the constant writing. That means a whole writing and whose words represent the digits of pi. A whole writing. Every word from the title of the writing and to the every words of this book or of this article actually followed the digits of pi. And this is one of the examples of that book, Not Awake. And in these books, you find that the 10,000 words that represent the digits of pi, every word. They said in this way that every digit actually represents some digits of pi. You can see here, not 3, 1 and 4, not awake. This is 3.14 and then 1, then 5, then 9, then 2 and then 6 and then 5 in this way. These all numbers are actually from the starting represent the digits of pi. And every word inside these books and from starting to the end, the whole books actually represent the digits of pi. So mathematicians or scientists actually take it as an experiment. You can take that. That they can do anything using that pi. So you might actually not use that pie in your daily life, but you can see this pie everywhere. Just see the building construction, quantum physics, this quantum mechanics or communication, music theory, medical systems, everywhere, travel and space theory, everywhere you can find this pie. So that's why I think all of you actually can build another views for this pie from today. That why Pi Days, we are celebrating this Pi Day, why this is important and how this numbers is embedded with us. Okay? And thank you all and happy Pi Day to all of you.
Thank you Milan sir for this wonderful deliberation. It was quite engaging and enriching with these details, these facts about pi. So it was, it set the stage perfectly for the presentations to come. I hope you are all charged up with the presentations. Yes? So